Hello and welcome back to my channel. If you haven't watched my last video, I highly recommend that you do, because in this video I will be covering a topic called the Cauchy-Schwarz inequality. I am now going to introduce to you a new form of Cauchy-Schwarz. Now you see, the sum of all a squared times the sum of all b squared is greater than or equal to the sum of both taken together, all squared. And this is exactly identical to this. I'm writing it in this way because the questions I plan on covering today are more sum reliant than the ones in the last video. So I'm going to replace this with this. Alright, now that we have our new inequality, let's get into it. And now our first problem is above the board. So although this problem looks really hard at first, what we have to do is square both sides of the inequality. Now since between 0 and 45 degrees, the sine of x and the cosine of x and the tangent of x are all positive, there is no need to switch the sign of the inequality. And so now we have the sum of 1 minus the cosine to the power of 4i over 1 plus the cosine of squared I, and then multiplied by the sum of 1 plus the sine squared of I over 1 minus the sine to the power of 4 of I. And then this is greater than the sum of tangents of I all squared. So at first, the application of Cauchy-Schwarz is not that clear here, but one thing we can do is manipulate these two expressions to maybe solve for some sets such that Cauchy-Schwarz can be applied. First of all, we look at 1 minus the cosine to the power of 4i. 1 minus the cosine to the power of 4i is equal to 1 minus the cosine squared of I times 1 plus the cosine squared of I. So then we can divide 1 minus cosine to the power of 4i over 1 plus the cosine squared of I to get 1 minus the cosine squared of I. But then notice that by the Pythagorean identity, this is equal to the sine squared of I. So then we get the sum of sine squared of I. But then for this, we can apply something similar here, because 1 minus the sine to the power of 4i is equal to 1 plus the sine squared of I times 1 minus the sine squared of I. So this is equal to 1 over 1 minus sine squared of I. But then 1 minus sine squared of I is equal to the cosine squared of I. So this is equal to the sum of 1 over cosine squared of I. This is then greater than or equal to the sum of the tangent of I squared. And now, the application of Cauchy-Schwarz is looking a little bit more clear now, because the two sets we're going to make is that the set A of I is equal to the sine of I. Also, the set B of I is equal to 1 over the cosine of I. But since the sine of I times 1 over the cosine of I is equal to the tangent of I, we have now proven the statement to be true, and so this is greater than this, and we are done. Alright, now on to the next problem. And now our problem is above me. So first, we want to figure out what is this summation up here, or what is the sum for 1 is lesser than or equal to I is lesser than j is lesser than or equal to 216 for all xi, xj. But then notice that j is strictly greater than I, so j cannot be equal to I. So we get x1, x2 plus x1, x3 all the way to x1, x216. Then we add x2, x3 plus x2, x4 all the way to x2, x216. Then we continue this until we eventually get x215, x216. Now notice that we have x1, x2, but no x2, x1. And notice that we also have no x1, x1, no x2, x2, no x3, x3, and so on. And so this sum is equal to 1 over 2 times the sum of xi all squared minus the sum of xi squared. But we know from the problem that this is equal to 1. So we have 1 over 2 times 1 minus the sum of x squared I. So now we can substitute this into the second equation in the problem. So first, we can factor out a 1 over 2 from the summation. So we can erase this 2 to get 1 over 2. Then we can multiply both sides of the equation by 2. So we can erase this 1 over 2, and we can erase this 1 over 2. Then we multiply the 107 by 215 to get 214 over 215. So now, let's start moving terms to the other side. So we can move this term over here to get 1 over 215. Then we can add these two summations together to get the sum of ai x squared I over 1 minus ai plus x squared I. Now we can combine these two to get that 1 over 215 is equal to the sum of x squared I over 1 minus ai. We're going to use this equation later, but for now, let's move it to the side. But then also, notice that the sum of 1 minus ai is equal to 215. So now we can apply Cauchy-Schwarz, taking the square roots of both of these summations, to get that the product of these two summations is greater than or equal to the sum of xi all squared. Now we know from the problem that this is equal to 1. So the product of these two summations is greater than or equal to 1. But we are looking for the equality case, so we can turn this into an equal sign. Now let's set up an equation where x of I is equal to y times 1 minus ai for some constant y. Now we can take summations on both sides to get that the sum of xi is equal to y times the summation of 1 minus ai. We can put y outside of the summation because y is a constant, so it doesn't affect the summation. Now we know that from here, this is equal to 215. So 215y is equal to 1 because all the sums of x's are equal to 1 from the problem. So we have 1 is equal to 215y, and 1 over 215 is equal to y. Now we can plug in 2 for I to get x2 is equal to y times 1 minus a2. Now we know that y is equal to 1 over 215, but what is the value of a2? Now, a of I is equal to 1 over 2 to the power of I, so 1 over 2 to the power of 2 is equal to 1 over 4. So substituting these values in, we get that x2 is equal to 1 over 215 times 1 minus 1 over 4. Now this is equal to 1 over 215 times 3 over 4, which is equal to 3 over 860. And now since 3 over 860 are relatively prime, our answer is 860 plus 3, which is equal to 863. And so, we are done. Alright, thanks for watching. Hopefully you enjoyed. If you haven't watched the first part of this video, be sure to check that out. And hopefully, I'll see you next time.